In this video, I'll talk about the physical properties of internal and terminal alkynes, and I'll also talk about the acidity of terminal alkynes. So the really one big difference between the internal and terminal alkynes is really the presence of the triple bond. In case of internal alkynes, you would have the triple bond somewhere in the middle of the molecule, like you can see right in this case here. And in case of terminal alkynes, you would have it at the end. So if I want to count the number of carbons in this first one, I would say I'll have 1, 2, 3, and 4 carbons. So the name for this would have been but 2 ine, or I can just say 2-butyne. Now, if I want to look at the second one is in a terminal alkyne where I would start counting from the right side because I want to make sure the triple bond gets the lowest number possible. So that would be 1, 2, 3, and 4. So this one I can call it 1-butyne, or just as in a simple, I'll just call it butyne because if it's at the first position, you don't need to specify the name. Now, one difference is obviously do not have the hydrogen connected to the triple bonded carbon in case of internal alkyne, but you do have that in case of terminal alkynes. So I would have an hydrogen onto this terminal alkyne here. And this hydrogen makes the difference because this is a little bit of an acidic, so you can easily remove it, and you can create a negative charge on this carbon, which could possibly act as a strong base and a strong nucleophile, and it can, depending on what you really want to do, you can go either way on that. Now, this next one, for example, this is still going to be an internal alkyne, so that would be 1, 2, 3, 4, 5, and 6. So we got 6 carbons in there, and that would make it hex 3 ine. Now, one more thing I want to mention here, whenever you come off from the triple bonded carbon, like you coming off from right here and right here, you draw a straight bond. And the reason why you draw the straight bond, because the triple bonded carbon is actually going to be an sp carbon, and around sp carbon, the bond angle is 180. So that's why you draw this in a straight line here. So just because you see in a straight line, don't forget that there is actually going to be a carbon wherever the triple bond ends, and then wherever it goes off from there, you're going to have another carbon here. If you don't draw anything off the triple bond, like for example, we didn't really draw anything earlier on this, that means you're just going to have a hydrogen connected to it, and you don't necessarily need to draw that hydrogen, but it's an automatic that it's going to be there. If there wasn't a carbon, I would draw in a straight bond here. So I'm just going to go ahead and put the hydrogen back in there. But once you come off from the triple bond, and once you kind of going down to 1 carbon, like this carbon 3 right here, now that carbon is not an sp carbon anymore, but rather that's an sp3 carbon. So that's why, so this one is an sp3, this one is an sp, and that one is also an sp carbon. So since this is an sp3 carbon, that's why you see an angle here, because around sp3 carbon, the bond angle is supposed to be 109. And that's what we have done in the other one here. So right where the triple bond is, once you go off from the triple bond, you draw in a straight line because the bond angle is going to be 180. But once you go away from that, and next carbon is going to be simple sp3 carbon that is going to give you a bond angle of about 109. So you have an angle drawn here. So that's something you got to be really, really careful with. Now, in terms of the physical properties, alkynes, they don't really have any polar grips, so the only type of intermolecular forces they would really be making would be the dispersion. So you know, if it's only dispersion forces, that would relatively give them lower boiling point, and that makes them insoluble in water. Because, you know, for something to dissolve in water or miscible or be miscible in water, you have to have a polar grips like OH or NH2 and stuff like that. But alkynes, you only have carbons and hydrogen, so that is just going to be the recipe for only dispersion forces. So if you have only dispersion forces, that kind of gives them relatively lower boiling points and insolubility in water. Now, obviously, if you increase the number of carbons, Like for example, I can say between this second butene here, or second alkyne I have drawn here, and then this third alkyne I have drawn on the right side, the third one would have a higher boiling point, and the reason is just longer, it's just bigger surface area. So more carbons you have, bigger the dispersion forces in that case, and that would just increase the boiling point in that particular case. But other than that, they both will be making dispersion forces. It's just that the compound on the right side is bigger in size, so it's going to be making more amount of dispersion forces, and as a result, it will give them a higher boiling point. Now, let's come back to the terminal alkynes, because in the terminal alkynes, you have this proton that's usually often a great interest. That proton, it has a little bit of an acidic nature. And the pKa of that proton, so if I'm going to go ahead and write that down here, the pKa of that terminal alkyne proton is about 25. So I need to have a base that's going to be relatively strong enough that can remove this proton. Now you can test which base is going to be relatively strong enough. So suppose if I run this reaction with a hydroxide and I want to test if that is indeed going to be able to remove that proton or not. So if I go ahead and run an acid-base reaction, I would grab this proton and I would end up going ahead and creating the negative charge on that triple bonded carbon here. So I'll get a negative charge here, and I have the water made. Now, to determine whether this equilibrium will be shifted to the right or to the left, I can compare the pKa's of the acid and the conjugate acid. So this is your acid, this is your base, this is your conjugate base, and this is your conjugate acid. Now, the alkyne's pKa is about 25. The water's pKa is going to be about 14 to 15. So, remember, a lot of books has 14, but some books also has 15.7. So it's really a matter of which reference you're really using. But regardless, it's way below than the 25. So what that tells you that the water, relatively speaking, is going to be in a stronger acid because it's got the lower pKa value compared to the alkyne. So this equilibrium is going to be shifted to the left side. So what that means that the OH minus and things like OCH3 minus and even like OCH2, CH3 minus, they kind of fall in the same ranges of the pKa's, somewhere around like 16, 17s when they make the alcohols out of them. They're not typically strong enough. So we don't really use those bases to deprotonate the alkynes, but rather you have to figure out something stronger that can actually deprotonate the alkyne. So the next one I can go ahead and pick. Let me just go ahead and copy this. And then I can also say the most common base that's used to deprotonate the alkynes. One of them is an NH2. So the NH2, remember when I write down NH2 1 minus, they typically write this down with the cation. So that could have been NaNH2, or that could have been something like KNH2. But I'm just writing the base here, not writing the cation with it. But typically you would see the cation being written with it. That just means you have the NH2 1 minus that you really worrying about here. So again, if I want to do a reaction here, so this lone pair is going to go and grab the proton here, and that's going to break the bond, and eventually I'll end up making 1 minus there, and I would have the NH3. So again, this would be your acid, this is your base, that's your conjugate base, and that would be your conjugate acid. If I want to look at their pKa values, alkynes is about 25. Amines or ammonia, they're going to be over 35, so somewhere greater than, I would say, 35, somewhere around 40. Some books has them, but just let's say somewhere over 35. So that kind of gives a huge difference in the pKa value. So since you have lower pKa value on the alkynes, that makes this a stronger acid relatively, and that ammonia would be in a weaker acid. So remember, your equilibrium always shifts to the weaker side. So this will be shifted to the right side. So that means this NH2 minus is actually strong enough to remove this proton. So that's one of them that is typically used. The other one that's typically used, I'm just gonna copy this for the sake of time. I'm just gonna copy this side here, and I'll erase. I'll just put this down. Just change this to a different color. Okay, so the other one that's most commonly used is actually the hydride. So the hydride would be the H1 minus, and the hydride when they write them, they would write them as an NaH or KH or LiH, something like that. And when I do the math here, the product here would be actually the hydrogen gas. So we already have the acid and bases kind of categorized here, the conjugate bases and all that. So the pKa values for this alkyne is 25, and the pKa value for the hydrogen gas is going to be, again, more than 30, almost more than 40, actually. It really depends on what reference pKa table you're using. But there is another advantage when you're using the hydrogen, and I think that advantage also stays with ammonia as well, because hydrogen is in a gas, so as soon as it's made, it actually escapes the liquid, so it kind of shifts the equilibrium to the right side according to the Le Chatelet principle. Because if you lose this, it's going to shift to the right side. So that's a plus thing on that. But then if you don't focus on that and just focus on the pKa's as well, that still helps because there is a huge difference in the pKa's. The hydrogen gas itself being in a weaker acid here, the alkyne is going to be the stronger acid. This is going to be shifted to the right side. So those are really the two most common bases that are technically used. So NH2, 1 minus, H1 minus, and occasionally you may see like LDA being used to remove the proton of alkynes as well. That's completely okay because remember, even though it's in an LDA, it's still in a nitrogen base. It's still in an amine based base, just like an NH2. All right, so it's just like in a bigger molecule, but you will still have in this molecule within a nitrogen negative charge, just like you have in an NH2. So you could use LDA as well to deprotonate the alkynes.